find a seat. We'll be starting in about 1 minute. In this session, please make sure that you're at the front of the room, and please come and find me. All right, we will now begin. Welcome to the DeepRL 2 session, which paradoxically actually comes before the DeepRL 1 session, but that's okay. Our first paper will be an investigation of model-free planning, and Arthur Ghez will be speaking.
Okay, thank you. I'm Arthur Ghez, and I'm presenting this work. This is joint work with Mehdi Mirza, Carol Gregor, Rishab Kabra, and lots of amazing collaborators at DeepMind. So we want our RL agents to tackle complex combinatorial domains. And I think it's fair to say that most of our agents at the moment really shine at reactive tasks. And by this I mean most of the difficulty of the task is kind of understanding the situation, like understanding that the current real state of things, and then kind of deciding what to do on top is kind of a little added difficulty. So, for example, in this kind of Enduro Atari game, if you can understand where your car is and where the other cars are, and this is a road and it's bending, then it's not too hard to kind of extract that you should be pressing right after that, and this is the correct decision. But we want to demonstrate more foresight and better generalization. We want our agents to the ability to plan effectively. And for this, kind of traditionally, people have gone kind of via model-based methods where there exists some kind of decomposition of the environment where we can maybe in robotics extract the states and use an existing simulator or learn the simulator and apply then some planning algorithm like search. And this has been like a really fruitful kind of area, and there's lots of work going on this front. More recently, there's also been attempts to kind of put knowledge about algorithms, about planning algorithms, inside the network via some inductive bias. So here, the idea is to kind of it's a bit like a differentiable algorithm if you want. You want to use all the structure of the algorithm, but you want to keep the flexibility of the network so that it can adapt to the data and deal better with all kinds of errors and so on. And yeah, so in this work, I'm going to basically compare a bunch of these, and there's going to be hopefully some surprising results as well. So here are some of these kind of hybrid neural network architectures I'm talking about that have been recently published. So for example, like without going into the details, for example, value iteration networks on the left here, which puts kind of dynamic programming inside the network. A3C and MCTS nets that put like tree-structured networks. And I2A that learns them all and then kind of encapsulates this in a model-free agent. So just to kind of motivate a bit why people have kind of looked at this kinds of architecture, let me talk about a concrete example, which I'll be using as a kind of a running example throughout the talk, is the Sokoban domain. So in Sokoban, I'm sure most of you know the domain, but I'll explain. So you're like this green, little green guy here, and you need to push the boxes on the red target. It doesn't matter which one. At the end, you just need all the boxes to be on targets. And you can only push the boxes. So the catch is you can't pull them. So that can lead to irreversible situations quite quickly. But notice that it's fully observed, simple dynamics and visuals. The complexity really comes from the fact that this combinatorial complexity here. So here on the left, I'm showing you a really easy level. You can probably solve in your head. And here, there's many ways to solve that one. Just take the nearest box, put it on the nearest target, and so greedy strategy, simple heuristics, that's going to be enough to solve these kinds of problems. But if we look at the problem on the right here, This one, unless you've played a lot of Sokoban, probably you won't be able to solve with just a few seconds. Requires a bit more kind of maybe a planning ability here. And the point is, if you modify small modification, like visual modification of the domain of this kind of pixel representation, is going to affect a lot the solution. This is in contrast to Atari, where if you change small perturbations, you can be robust to that by generalizing in kind of this representation space. Here, the kind of generalization we require is much like a deeper kind of generalization. It's about what it means to, what these actions mean and what the consequences are in the long term. So because I'm talking a lot about planning, I realize this is kind of a bit of a loaded term. So maybe it's kind of useful to take a moment and reflect about the definition. And often people have associated planning with the mechanism at play here. So model-based methods and search, this is kind of what we consider kind of planning methods. And this is what gets you kind of the foresight and the flexibility. But here we want to be kind of a bit agnostic about the method and just say, like, what do we want from planning agents, and just care about kind of the effect. So for this, we looked at behavioral characteristics of planning. So we're proposing this kind of three axes, related axes of for an agent to be planning. One of them is on the left is kind of the ability to generalize in combinatorial spaces. So this is that you basically in places you want to be doing well, in places where memorization is not enough. If you can kind of figure out if you have a good planning solution for a domain, then maybe this is kind of the second one. Then if you have a good planning solution, if you can solve some mazes, then hopefully given enough resources, you should be able to solve other mazes as well, or most of them. And that ties into the third aspect, which is about time scalability. If I give you more resources, then more computation, you should be able to do better without seeing new data. So the ability to ponder. Okay, so now the question is whether model-free methods can fit that definition and exhibit kind of this kind of behavioral characteristics of planning and get you the foresight and so on. So in this paper, this is our investigation. We considered planning domains, mostly procedural. So every episode is roughly a level. We trained different kinds of neural network architectures. Some of these kind of hybrid architectures I've talked about, like value iteration networks and I2A, and other kind of off-the-shelf neural networks like ResNets and CompNets. And we also propose a new architecture here in this context. And we observe performance, generalization, efficiency, and so on, and these kind of properties that are related to planning I've just outlined. Okay, and briefly, in terms of the methodology to test this, we kind of fix a single algorithm, which is essentially a variant of Impala vtrace. So this is an actocritic algorithm. And with that same algorithm, we vary the neural network architecture. So basically what goes in the blue box here. So we get an observation at MT, maybe there's some dependency on the past if it's a recurrent network, and we output a value and a policy at each time step. So let me show you some of performance of some of these methods on Sokoban. Here, what I'm going to show you is kind of training curves that are a function of number of training steps, and on the y-axis is the fraction of solved levels on the test set. So these are levels that were never seen during training by the agents. And just to give you a sense of what that y-scale means, I've kind of outlined a rough kind of explanation here, where you see kind of roughly 40% of levels are kind of quite easy in the sense that as a human, something like a really greedy strategy would get you to solve the levels most of the time, so that would require like no thinking. And then kind of the medium levels, that would require like this kind of local traps to avoid. You have to be a bit careful locally about like some combination and so on, so that would require probably like a couple seconds, even like 30 seconds of thinking in some cases. And then if we go to hard levels, that probably would require as a human like a couple retries or a minute of thinking. And then kind of the hard levels, if you're not a Sokoban player, probably you would think they're impossible. Okay, so here are some of the methods we looked at. So the specialized methods for planning I2A and VIN and A3C. So I2A was kind of previously the state of the art for learn RL models for this task. And here, already the big takeaway is like just taking off-the-shelf architectures like ResNets and CNNs and kind of scaling them if you fine-tune them in the right way with modern RL frameworks, they can actually do better than specialized architectures in this domain. So partly inspired by this, we decided to kind of also assemble some of these off-the-shelf components, but in a way that maybe was more appropriate for planning. And then we designed this architecture DRC, which does a lot better on these kinds of tasks, Sokoban and other planning domains. So this both learns much faster, but it also gets better performance at the end after training. So even though that looks like a small difference here, this is kind of, it's doing 4 times less failures on the levels that are hard. So it actually is finding a much more general solution to these levels. So let me describe what this architecture is, and then I'll provide a bit of motivation for it. So let's start with the stacked conval-STM for an actor-critic architecture. So here, there's some encoded input, and we have d equal 2. So d is an hyperparameter in this case. So we stack 2 conval-STM modules. So these are these little colored squares. Conval-STMs are, just as a reminder, they're kind of a special form of LSTMs with convolutional transitions and spatial representation of states. And here, the parameters are not shared for the different representation levels. So we stack, d conval-STMs, and then we process the final output to output the value and policy. Now, we can repeat within the same time steps that conval-STM. So we repeat it. So this is another hyperparameters n. We repeat n times the same conval-STM modules. And so this is kind of what we call the deep recurrent conval-STM architectures. There's a few more bells and whistles in the paper, but this is really the gist of it. And we abbreviate this to DRC DN in the rest of the talk. Okay. And of course, because this is a recurrent network, there's also ticks iterations from previous time steps that come into play here. And notice, like, this is the important point. This wasn't inspired by a specific planning algorithm. There's no planning algorithm that we used to kind of design this. The motivation here was to kind of force repeated spatial computation before coming up with an output. And let me say this in a different way, like that. Maybe one common view of RNN in RL is to use the RNN mechanism as a way to filter past information and kind of just gather like the important bits of information from the past that are really useful for the present as a memory mechanism, and then combine this with some representation learning in yellow. This is doing maybe the heavy lifting and then combining that information to come up with the output. But here, in our domains, there's no memory requirement, and the visual appearance is quite simple. So what we're really after is something more akin to this, where we just want to use, we want to do amortized planning and use all the previous time steps to kind of slowly build a plan and encourage the network to find like this kind of modular solution to the planning question. So coming back to trying out different versions of this DRC architecture on Sokoban, something that's pretty clear here, so this is in early training, is that both the stacking and repeating is important. So the DRC, what was particularly useful, like what worked quite well across experiments and domains was to repeat it 3 times and stack three of these modules. And that performed really robustly across domains. So now I'm going to a bit more systematically look at questions of generalization and data efficiency. So one study we did in Sokoban, again, was to vary the dataset size, so the number of levels that the agent is exposed to. So this is in the color on these curves. And we vary the network capacity, so this is top versus bottom. So there's a couple of things to extract from this, but let me just outline a few. So one of them is that even when you have only 1,000 levels, the large network overfits a lot less. So you can see here that on the test set, when it's only been trained on the 1,000 level, it can achieve more than 60% performance. So that means from just the 1,000 levels, it's extracted a solution that can solve non-trivial levels. On the other hand, the smaller network just can only barely kind of solve the really trivial ones. And if you go up to 10,000 levels, this is the orange curve on the top, then the generalization is already pretty good in the sense that you can get 90+ performance on the test set by just having seen this kind of 10,000 levels. So if you already kind of understood a great bit about how Sokoban works and should be solved. In terms of time scalability, what we've looked at is basically taking the network after training with fixed weights and adding a way to kind of do pondering. So what we did for this is force no ops at the start of episodes. So this is what I'm showing on the x-axis. And on the y-axis, I'm showing you, how much better does it get, basically, when you add these extra steps of computation. So for DRC, we found that this kind of significantly improved the performance. And so, this is kind of a sign that there is this kind of amortized computation and pondering that's going on in the solution I found. We didn't find this to be the case for flat LSTMs. I don't think it doesn't mean that LSTMs are not capable of doing this. It just means that in this instance, the solution it found wasn't kind of the kind that you could iterate and do better. Finally, we've done experiments like in Sokoban in other domains such as Boxworld, Mini Pac-Man, 2D navigation like in the Vin paper and some Atari games, but I'm not going to cover them in this talk. But we also get basically essentially similar results across these domains. We also are releasing Sokoban dataset with levels of varying difficulty and trend and test sets splits. So these are on GitHub. So some takeaways, we found that model-free methods can exhibit some striking planning behavior. We can learn to amortize computation over multiple time steps in an RL setting. We did not find inductive bias to be useful to help in these situations. It doesn't mean that kind of these hybrid architectures are a dead end. It just means that we need to work harder on how to tune them and fine-tune what exactly these are doing. The DRC architectures was surprisingly efficient, we found, and robust in these 2D domains. There's more control experiments and ablations in the paper. I'm going to take some questions, but I just want to leave you with this video of a good agent solving medium difficulty levels in Sokoban. Thanks.
All right, we have a few minutes for questions, so please come to the microphone.
Hello. Did you compare with model-based approaches where the model would have to be learned as well?
So there's a couple of things we did. So I2A, the I2A, I didn't have time to explain in much detail, but I2A is a method that's kind of model-free and model-based at the same time, in the sense that it learns a model, and then within the architecture does some Monte Carlo rollout, and then aggregate this as featured. But the outer thing is still a model-free algorithm. We also compared in the paper to state-of-the-art kind of classical search methods that use neural networks as priors and so on within them. And these, of course, if you give enough computation, they can scale arbitrarily, but they're quite expensive. So I think we're faring quite well compared to them. If you do naive, even like if you use the true model, naive MCTS, it requires quite a bit of tweaking and network priors and so on to make them work nicely in Sokoban.
So you mentioned at the beginning that it would be desirable if given more computation, you could get better results. Did you train for that or test that by varying n sort of on the fly?
No, so so just to clarify, in this experiment that we did, there was nothing special in the training scheme. Like it's really, we trained as usual, and then we fixed the weights, and then just looked at adding more compute by this special action in the environment which does nothing. So we just force that action. We force the agent to take this action multiple times. So the network is ticking all this time, and then the episode starts. So here this is.
So can it decide to use more computation?
So it's forced to use more computation, but then the question is whether that's useful to the performance. So because the network is ticking without anything going on in the environment, and then you can start doing things. Is that, yep.
Okay, I really liked the definition of planning. One thing that's kind of striking about the symbolic approaches is that there's this hierarchical aspect to it, that you can reuse these small strategies. So I'm aware that's not method agnostic, but is there a way to kind of transfer that into method agnostic language?
Okay, can you clarify the question? Sorry, I think I've...
So like the old style planning, the thing that it did really well is that you could define these little operators that weren't tied to a specific reward function and reuse them, right?
Right. Yeah, there's definitely, I mean, so to some extent, these networks probably find like little bits of solutions that they, small heuristics. And then the question is whether at which level these heuristics operate. Like, are they kind of really at the local representation level, or are they at a really kind of high level that's useful for this kind of deep generalization we're after? So we haven't tried to kind of, really kind of be quantitative about this, but I think that's a really rich area for future work and kind of maybe define more clearly what these concepts are, like such as planning. Yeah.
All right, let's thank the speaker one more time. The next presentation is entitled Curious, Intrinsically Motivated Modular Multi-Goal RL, and the speaker is Cedric Colas. There we go.
Thanks. So in open-ended environments, autonomous learning agents must set their own goals. They must build their own curriculum using an intrinsic motivated exploration. So agents might face a huge diversity of potential goals, and they might want to discover which goals are controllable in the environment and which are not. So because some goals are easy and others impossible, agents need to actively select which goal to pick at each moment in the environment. So here our agents might face a huge variety of goals. They are organized into modules, or goal types. So they can decide to reach a particular position in the environment, to push cubes on the table, pick and place cubes, stack cubes, and so on. And for each of the modules, they have to pick a particular goal. So they can pick and place at position X, or reach at position Y, for example. So because they set their own goals, some might be really easy, like moving the end, and some might be impossible, like pushing the out-of-reach cubes. So that's the overall setting. Now let's look at our contributions. So the first contribution is to combine universal value function approximators with a new modular encoding of the current goal, so that the agent can target multiple goals from multiple modules, all inside a unique controller. The second contribution is to use the absolute learning progress measures to bias the selection of goals to targets and also of goals to learn about using insight learning. So learning about all goals from all modules inside the same controller enables efficient generalizations across the different goals and enables faster learning when compared to having a multi-goal expert policy per module. So let's have a look at how the agent uses learning progress measures. So on the left, you have the evolution of the average success rates computed over each module as subjectively perceived by the agent, so the subjective competence measures. And in the middle, you have the corresponding absolute learning progress measures. And on the right, you will have the goal selection probabilities computed using a bandit algorithm based on the learning progress measures. So how does that work? First, the agent makes some progress on the reaching task in blue, which triggers some interest in that task on the right. After a while, it masters the task, the module, so progress drops and interest drops as well. Whereas the interest in the pushing task in orange starts to grow because it gathered some rewards. So why is it a good idea to use learning progress? It builds some kind of resilience to distracting goals. Most of the goals in the world are not possible to do, so the agent can detect that it doesn't make any progress and reallocate its resources on other goals that are more learnable. So when the proportion of those distracting goals in the environment increases, our active learning agents will be more and more efficient compared to the random goal selection baseline. Another point is that it builds some kind of resilience to forgetting and sensory failures. So here in the black line, we triggered some kind of time-locked sensory perturbation in the robot, which affects one of the module. And the agent is able to detect that a performance drops on that module. It is able to refocus on that module and regain control of it twice as fast as the random goal selection baseline. So overall, we presented an intrinsically motivated agent that is able to use learning progress measures to bias the selection of goals to targets and to learn about using inside replay, and is able to do all that inside a unique controller, so targeting all the goals from all the modules. If you want to know more about that, you can come have a chat at our poster tonight, number 42 in the Pacific Ballroom. Thank you.
All right, the next presentation is called Task-Agnostic Dynamics Priors for Deep Reinforcement Learning, and Yilun Du will be presenting.
Hi, today I will present on our work on using learning task-agnostic dynamic priors for deep reinforcement learning. So we are motivated by 3 questions. So the first question is, can we train our agents to learn physics in a task-agnostic fashion? And furthermore, if we learn such task-agnostic priors, does it help in RL? So the reason for this is, as humans, we have some intuition about how things will act, and based off this, we can apply this to a wide variety of tasks. So in the games on the right, you can see that despite them being very different things, we can learn to play each game very quickly because we understand the physics underlying them. And finally, we wish, can we transfer and learn the physics knowledge from one environment to another? So previously, when training dynamics models in R primarily, they focus on action conditional dynamics models, which make it very difficult to transfer across environments. Otherwise, they focus on parameterized physics models, but these models require manual specification for each task. So in our work, we learn physics priors by training through a large amount of task-independent data, where we learn to predict the data in an action unconditional manner, and we add local inductive biases in the architecture to learn the local nature of physics. So our overall approach is to pre-train a frame predictor on physics videos, and then initialize a dynamics model using this, and then simultaneously fine-tune the dynamics model and the policy on a target environment. So our network that we use to enforce the physics biases is spatial net. So essentially, the blue blocks represent encoding blocks of convolutions, and the green blocks represent deconvolutions. And we have a central spatial memory module, which is a 2D grid. Specifically, the spatial module basically is a 2D grid of state. So it's kind of similar to the conv-LSTM model, except we use convolutions throughout the architecture and residual connections to better model dynamics. And the reason why a 2D grid-like memory is nice is that you can store all the dynamics information of each object locally, and then dynamics can also act in a local manner. So as a visualization of what the spatial memory looks like, given input frames at the bottom, the spatial memory assigns information where each object is. So for our experiments, we evaluate, so we pre-train on a large data set of physics videos, which are 625 frames of moving objects, and then we evaluate on a set of physics PhysWorld, which is a set of 2D and 3D physics-centric games, as well as Atari, stochastic version of Atari. So to train our RL agent with a model, what we do is we take the future frames predicted from our model and feed it in as additional context with the past frames to train a policy. And crucially, we use the same prior learned from the physics videos across all tasks. So in terms of MSE loss, our method is able to generate much lower MSE loss than other methods, and also loses objects slower. Unfortunately, the video is not playing, but the next 3 frames are model predictions. It's able to kind of infer the movement of objects. So in terms of learning physics parameters, we find that by fine-tuning on a physics data set, our model is able to learn the best physics parameters, what we do is we train a linear layer on top of the spatial memory and try to regress the drag and elasticity of a scene. So we see that our pre-training on physics videos leads to best predictions, and also that learning on physics videos is much better for learning dynamics than like learning in Atari or random initializations. We evaluate, so in terms of physics environments, this is one particular one called PhysShooter. Essentially, our method in green performs better than PPO, which is in blue. And furthermore, our method also outperforms a series of other model-based methods, such as I2A in green. We also evaluate on Atari, where orange is the performance of our method and blue is the performance of PPO. So we find that our method outperforms PPO on 8 of the 10 environments that we selected. And also in terms of transfer learning, our model allows us to transfer between different environments. So we find that just directly transferring model sometimes performs better than model and policy transfer. So yeah, overall, these provide a useful series of solutions for improving sample efficiency. You're welcome. If you are interested in more, please come to our poster at on number 43. Thanks.
All right, the next presentation is called Diagnosing Bottlenecks in Deep Q-Learning Algorithms, and will be presented by Justin Fu.
Hello, my name is Justin, and this is joint work with Avril Kumar, Matthew So, and Sergey Levin. So Q-learning methods have gained a lot of traction in recent years, but they're still notorious for being very hard to use. For example, I can download an implementation of DQN and run it on a simple environment like Cartpole, and I would expect the performance to be stable, but if I use out-of-the-box hyperparameter settings, I can sometimes get learning curves like those to the right, which crash and relearn. So there are many reasons why Q-learning might be unstable, based on both theoretical insight and intuition. So the goal of this work was to empirically verify these claims in practice in order to better understand Q-learning methods, highlight effective design choices, and future directions for research. We evaluate by controlling for specific approximation errors in tractable domains, and we verify that many of the trends that we see continue to hold true even on deep RL problems. So the first problem we look at is the interaction between function approximation and convergence. So function approximation has long been cited as a reason for instability in Q-learning. We find that when isolated, function approximation actually does not tend to cause unbounded divergence. Instead, the bias that you would get from using weak approximators is amplified. So in this figure on the right, the orange bars represent the error of the best solution in model class. The green error bars represent the error of the solution found by Q-learning, which is typically much higher. The good news here is that deep learning is actually very effective for tackling this problem because we can easily use approximators with high capacity to let us stay in this low error regime. Next, we look at overfitting and sampling error when minimizing the Bellman error. So while large architectures are more susceptible to overfitting, we find that they tend to do better. And we think this is because the bias is amplified, so its effect is greater than you would normally be used to in a problem like supervised learning. However, it's still very easy to train too much on the data that you collect. For example, if you use an online method and you take too many gradient steps per sample, you can overfit and your performance can crash. However, if you take too few samples, you can underfit and learn too slowly. So normally there's some sweet spot that you have to find with hyperparameter tuning. You can automate this a little bit. For example, you can define an early stopping metric based on something like validation error, and you can get a moderate performance boost with less tuning. Next, what sampling distribution should you pick? So a lot of community insight dictates that you should sample on policy, and on policy is better. However, we find that in many cases this is not true. So for example, in many scenarios, just directly sampling from the replay buffer can result in better performance, and this is even when accounting for the number of samples that you're allowed to take. And the more general trend is that distributions which are more uniform and have higher coverage over the state space result in faster and more stable learning. So we've also released some recent work on making Q-learning less sensitive to the input data distribution, which we're happy to talk about more at the poster. Finally, we use some of these insights to develop a new sampling scheme, which we call adversarial feature matching. So this is formulated as a minimax game between the sampling distribution and the Bellman error with a feature matching constraint. So the scheme aims to reduce the effects of approximation errors by prioritizing states with high Bellman error while making sure that the features remain relatively independent across states. So we find that this scheme yields generous performance improvements on standard continuous control problems. So in summary, we've identified several aspects of Q-learning which we believe are underappreciated and warrant future exploration. So if you'd like to find out more, please come check out poster number 44.
All right, the next talk is entitled Collaborative Evolutionary Reinforcement Learning, and Shaharda Khadka will be presenting.
Hello. Let's start with a simple sort of depiction of a normal learner. You have an actor, you have a critic, you have an algorithm, which is just the update rule, and we have a bunch of hyperparameters. And the actor samples sort of explores the environment, collects experiences, puts it in the buffer, and learns from it. I'm going to call that entire block learner, henceforth, just for simplicity. Now let's sort of look at what this learner actually optimizes, right? What does it optimize? It learns to optimize this, the return, which is a discounted sum of rewards in the future. And what basically this means is like you kind of care about the reward closer to you more than the one in the future. The degree to which you do this is sort of controlled by that discount factor or gamma. In other words, if the gamma is low, you're sort of a short term, you're like more greedy. If the gamma is high, you're sort of a long-term optimizer. Gamma controls the resolutions of the task, the resolution at which you try to tackle the task. So based on that, what we do is we take what we had, this setup, and just do this, an ensemble of learner that has different gammas. So basically what you have is a portfolio of learners that optimize the same task over different resolutions and share information amongst each other using the shared replay buffer. Now, why do we do this? Consider Doom, right? Let's say if you have 20 more seconds to play, or like a minute to play, versus you have 3 more seconds to play. Does your preferred action change? Yeah, if you have like a whole minute, you're probably more conservative with your life, with your ammo. If you have 3 seconds, you'd probably just go out blazing. Simply by changing the resolution over which I asked you to optimize over the same task, your preferred action changed. And by extension, the exploration that you do and the space that you encounter. Additionally, consider this like a car sort of drifting a sort of turn. Sorry, the video didn't play. If you have a long-term optimizer that's trying to optimize over like, let's say 10 laps, would it ever try this move? No, because it's too risky. But if something looks at only the next 3 seconds, then it will, simply because it's more braver. In other words, failing is not as big of a fear for it, which sounds heartwarming, but at the end of the day, it's going to fail. It's going to crash again and again and again. But that's the thing about failure. If you fail a lot of times, which is a very risky proposition, you might just succeed. And when you succeed, things change. The bigger learner, like the long-term learner that did not ever try this method before, now sees that you have succeeded. In other words, because you have the shared replay buffer, right? But now once you've succeeded, it's not as risky. It didn't try this because it was too risk-averse. But once you succeed, it's not as risky anymore. Now it's going to subsume this skill onto its policy. So having this portfolio of learners doesn't only lead you to sort of explore different parts of the reason, but also sort of exploit collectively the things that you see, and also then distill and stitch these skills, the best of the skills that you learn, onto a singular policy. So that's back to the portfolio learners that we sort of developed. We have a couple of items that get additional, like added onto this to sort of make the entire framework. The first one we call a resource manager. What this does is it sort of, you can think of this as an online dynamic algorithm selection that does, that basically treats the whole portfolio as sort of like a stochastic multi-arm bandit and uses UCB to prune them. In other words, as a designer, you don't want to sort of select the gammas really carefully. Just put a good distribution there. It's going to prune it online as you learn. Makes it more scalable. And lastly, we have neuroevolution, which sort of combines this entire gradient-based optimization framework with a gradient-free optimization framework, which also, because it has a population, it sort of makes the whole thing stable. In other words, it builds in redundancy. And also, finally, it also sort of gives you another sort of axis of diverse exploration simply by having a multi-point sort of search method in the parameter space of the agents. This collective ecosystem of learner is what we call CERL, and you notice that it's a Lamarckian ecosystem where you have a gradient-free method and a gradient-based method learning concurrently. So one of the highlight experiments that we tested this on is humanoid, and we basically compared it against all of its composites. All of the learners that I described was part of CRL, tested in isolation, basically a self-contained ablation experiment. And what we see is CRL, the collective, can solve the task under, like solve humanoid under 1 million samples, while all of the composite learners with the same samples fail to solve the task. And it's important to note that the population-based method, the samples are counted cumulatively to make it fair. So what this sort of like shows is like the old adage of united we stand, divided we fail. Thank you. Poster number 45 later tonight.
All right, the next presentation is, okay, let's try to see if we can do that really quickly. The next presentation is entitled EMI, Exploration with Mutual Information, and Hyung-Suk Kim will be presenting.
Sorry. Sorry for that. Hello, my name is Jae Kim, and I'm here to present EMI. This is a joint work with Hyung-Suk Kim, Yeonu Jung, Sergey Levin, and Hyunho Song. And let me start with the motivation for our work. In this parsed word environment example, the agent should move from the initial position 1 to 6 without any guidance in order to get the first reward signal. Likewise, in sparse reward environments, the RL agent needs an effective way to explore the environment. Our approach to this problem is to embed states and actions to a low-dimensional space and determine the novelty of states the agent encounters with the embedding representations. And this figure is a visualization of a sample trajectory in the state space on the left and our learned embedding space on the right. Each number corresponds to a state at a specific time step in the trajectory. And let's move on to methods. EMI learns two embedding functions, phi and psi. Phi and psi map states and actions to the same embedding space with d dimensions, and alpha and beta are their parameters. We set the two criteria for learning the embedding functions. The first one is that given phi s and psi a, the uncertainty of phi s prime should be minimized. Also, given phi and phi s prime, the uncertainty of psi a should be minimized. Then, we can express those criteria in terms of Mitchell information. We maximize these two values. First, the Mitchell information between phi s and psi a and phi s prime. And second, the Mitchell information between phi s and phi s prime and psi a. However, it is intractable to directly compute the Mitchell information between two sets of samples from unknown distributions. Therefore, motivated by MINE, which is short for Mitchell information neural estimation, the lower bound of Mitchell information can be computed as this formula. And T omega is a differentiable transform with parameter omega. And this specific bound is based on the Donsker-Vardan representation of the KL divergence. Furthermore, motivated by deep Infomax, to derive the lower bound of Mitchell information, we replace the KL divergence with Jensen-Shannon divergence as a measure between the joint and the marginals, since it provides better numerical stability. We employ Jensen-Shannon divergence here because A, we are interested in maximizing the Mitchell information, not the exact value, and B, the KL divergence and the Jensen-Shannon divergence between the joint and the marginals of random variables x and y have approximately monotonic relationship. And Please note that we derive the lower bound of Jensen-Shannon divergence with a constant multiply to it. So the lower bound of mutual information using Jensen-Shannon divergence is derived as this formula, where SP denotes soft Plouffe function. And it's called the variational divergence lower bound of mutual information. And here is the proof of the bound. We can go from the first line to the second line here by using the definition of F divergence, where F is JSD, and expressing JSD with the Fenchel conjugate of JSD, which is JSD star, then followed by application of Jensen's inequality. The third line is obtained by substituting SXZ and JSD star with their definitions here. S is chosen to take care of the domain of the Fenchel conjugate and to allow T to output any real number. By applying the lower bound of mutual information with Jensen-Shannon divergence, our criteria for learning the embedding functions phi and psi are expressed as these two. T omega s and T omega I are neural networks with parameters omega s and omega a. And intuitively, you can see that the networks T omega s and T omega a are encouraged to output larger values for repeated samples and smaller values for novel samples. And from here, we'll see the architecture diagram of how EMI performs the mutual information estimation given a mini batch of transition samples. It builds the joint samples using the first half of the mini batch and computes the output of T omega s and T omega a for the joint samples like this. And the combination of the marginal samples are built by mixing samples from the first half and the second half, and the outputs of the T networks for those samples are computed like this. And the final step is to compute the estimation of the mutual information formulations. And in addition to the mutual information criteria, we apply another criterion for the embedding learning in order to make it possible for the EMI agent to measure the novelty of visiting states. We encourage the embedding representations of states, actions, and the corresponding next states to obey a linear dynamics that phi s prime is close to the sum of phi s and psi a. We offload the complex nonlinear aspects of the original environment dynamics to the embedding functions phi and psi. However, regardless of the expressivity of neural networks, there exists irreducible errors under the linear dynamics model. For instance, it would be extremely challenging for the linear dynamics model to express state transitions that lead to entering a different room or bumping into a wall. Therefore, we introduce the error model, which estimates the irreducible error given states and actions under the linear model. The embedding learning under the linear dynamics with modeled errors is expressed as this problem, where the estimated error and the embedding representations of states, actions, and the corresponding next states are stacked and denoted as the matrices. Combining all the criteria we've defined, this is the final learning objective for EMI. The first term minimizes the linear dynamics error, and each of the two terms from the second line penalizes the norm of the modeled errors and maximizes the lower bounds of the mutual information formulations, respectively. And lambda error and lambda info are hyperparameters that control the relative contributions of the linear dynamics error and the immature information term. And thanks to the linear dynamics model with modeled errors, EMI measures the novelty of visiting states with prediction errors under the model. For a given transition ST, AT, ST prime, it provides the prediction error for the transition computed by the linear model as the corresponding intrinsic reward. And this is the pseudocode for EMI. It first initializes the parameters at the beginning. And at every iteration I, it collects n samples with the policy pi theta. Then it computes the prediction error intrinsic rewards for the collected samples. And then it performs mini-batch updates on the parameters using the RM update rule to minimize the final learning objective. And at the end of each iteration, it updates the policy pi by augmenting the intrinsic rewards computed earlier with the environment rewards using any R method. And note that the prediction error intrinsic rewards are computed before updating the parameters for the embedding learning, because training on the current samples will make the intrinsic reward signals less diverse for the current samples. And let's move on to the next section, experiments. We compare EMI with 5 exploration baselines using TRPO as the policy gradient method. EX2 trains an ensemble model that estimates state visitation densities and leads the agent to less visited states. And ICM uses the forward and inverse dynamics models and forms intrinsic rewards for exploration based on prediction errors. And R&D uses 2 neural networks. It trains one network to predict the output of the other fixed randomly initialized network and employs the prediction errors as exploration signals. ICML trains an autoencoder and uses it as a hash function for input states. Then it generates count-based exploration signals with the hash functions, hash code. And FIME approximates the environment dynamics and employs the information gain of the learned dynamics model as intrinsic rewards. And to evaluate the exploration methods, including EMI and the baseline methods, we ran experiments on sparse word environments. For locomotion tasks with continuous control, we used swimmer gather and sparse cheetah from Bujoko. And for vision-based tasks with discrete control, we ran experiments on 6 Atari environments: Freeway, First Bite, Venture, Montezma's Revenge, Gravitar, and Solaris from arcade learning environment. And these images are example scenes from Swimmer Gather, Montezma's Revenge, and Venture. And these 3 plots are average return plots on locomotion tasks, and EMI corresponds to the red lines. Each solid line denotes evolution of the mean reward of 5 seed runs over training iterations. And the shaded area represents plus or minus 1 standard deviation from the mean. A and B compare EMI with the 4 baseline exploration methods on Swimmer Gather and Sparse Chira, respectively. In the 2 environments, vanilla TRPO, ICM, and R&D got almost no reward signals, and EMI outperformed EX2. And C here shows the evaluation study of EMI on sparse cheetah. Without the mutual information maximization objective, the EMI agent fails to explore the environment enough to get the rare extrinsic rewards, since the learned embedding representations collapse easily. It also shows that even with the mutual information maximization term, The linear dynamics and its error model play important roles in the exploration of the EMI agent. And next, these 6 plots are average return plots on 6 vision-based tasks from arcade learning environment, and EMI is again the red lines. These are the results of 5 seed runs, and each solid line is the mean reward over training iterations. The shaded area, again, represents plus or minus 1 standard deviation from the mean. And on these vision-based tests, EMI outperformed TRPO EX2 and ICM on First Bite and Montezma's Revenge, and showed competitive performance with R&D. And this table compares the final average returns of the exploration methods. In addition to EMI, EX2, ICM, R&D, and TRPO, which were shown in the average return plots, a SIMHASH and VIME columns with the results from the original papers are added. The R method used for all of the results here was TRPO. And we can see that the EMI outperformed or performed competitively on all of the environments except for Solaris. And from here, we'll show you state embedding representations learned by EMI with example trajectories on 3 environments. And note that since we use the embedding dimensionality of 2 on all of the environments, the visualization didn't involve any dimensionality reduction techniques. This first environment is Percept Cheetah. The figure shows that the learned embedding representation successfully preserves the similarity in the observation space. The next environment here is Montezma's Revenge. It shows that the embedding space naturally separates the state samples into 2 clusters, each of which corresponds to different rooms. And this is for Frostbite. As you can see, functionally similar states are close together and distinct states are far apart in the embedding space. In conclusion, we presented EMI, an exploration method that maps states and actions into the embedding space without relying on generation of the full observations. And our experimental results show that EMI transfers to a wide range of challenging tasks, including locomotion tasks and vision-based tasks. And the source code for EMI is available at github.com/sunumllab/EMI. And finally, if you are interested in further details or discussion about EMI, please come to our poster at Pacific Ballroom number 46. Thank you.
All right, we have a few minutes for questions, so please do come up to the microphone and ask a question. Okay, well, I can lead off with a question, although I might already know the answer to this. So you mentioned that the embeddings you showed had a dimensionality of 2.
Yeah.
Can you discuss a little bit how you think that the dimensionality of the embeddings would affect either the geometry that they learn or the results?
Actually, we tested with the embedding space with a higher dimensionality, and it showed a slight performance improvement. But we stick to the embedding space with dimensionality of 2 because it provides a better interpretability, and B, because of the computational efficiency.
Excellent. Does anybody have any other questions? All right, wonderful. Let's thank the speaker one more time. All All right. The next talk is entitled Imitation Learning from Imperfect Demonstrations, and Yu-Hua Wu will be presenting.
Hi, everybody. Hi, everybody. I'm Yu-Hua Wu from National Taiwan University, and I'm here to present our work, Imitation Learning from Imperfect Demonstration. So what is imitation learning? The goal of imitation learning is to learn an optimal policy from the demonstration generated from that optimal policy. The demonstration we talk about here is a set of decision makings, which is also known as the action pairs. But the problem is that the collected demonstration may be imperfect. For example, if we want to train an autonomous driving car, but there is some traffic violation in our data set, then it learns to make those traffic violations. So our motivation is to utilize confidence. Confidence describes the quality of the action pair, and it is a value between 0 and 1. But labeling confidence also needs some cost. So we adopt a semi-supervised setting that only a limited number of demonstrations are equipped with confidence. So how do we label the confidence? There are two potential approaches, like crowdsourcing or weekend labeling with digitized score. So there's a state-of-the-art imitation learning method called generative adversarial imitation learning. It considers the case that the given demonstration is optimal. And we would like to extend this work to imperfect demonstration. So our problem setting is as follows. We consider that the given demonstration is a mixture of demonstration from an optimal policy and non-optimal policies. The reason is that humans switches to non-optimal policy when they make mistake or are distracted. Therefore, we can represent the confidence RFX as the probability of y equals to 1 given x. We propose two methods. The first method that is because we only have limited number of confidence data. So we estimate the confidence score for the unlabeled demonstration by learning a confidence scoring function G. And the step 2 is to employ importance weighting to reweight Gale objective. So here's the first method. So the second method, the key idea of the second method is that instead of using confidence score to estimate the P optimal, can we use the confidence score to estimate P non-optimal? So we mix the agent demonstration with the non-optimal one, and we got P prime. And in our paper, we show that by matching P prime and P, we are able to learn the optimal policy. So here's our experiment setup. Our experiment setup is basically the problem setting. So in our experiment we use 20% of labeled data. And as you can see, our model significantly outperformed those baselines method. We also want to know, does unlabeled data really help? And is our method robust to noise? So as you can see, our method unlabeled data can make the variance of the performance lower, and they can increase the performance. And our methods are also robust to noise. So here's the conclusion. The main contribution of our work is that if the given demonstration is imperfect, our method is able to incorporate both unlabeled and confidence data to learn a better policy. If you're interested in our work, please come to poster number 47. Thank you.
The next presentation is entitled Curiosity Bottleneck, Exploration by Distilling Task-Specific Novelty, and the presenter will be Youngjin Kim.
Hi, I'm Youngjin Kim from Seoul National University and NRB. This is a joint work with Won-tae Nam, Hyunwoo Kim, Ji-yoon Kim, and Gunny Kim. The goal of this work is to propose an exploration strategy when observations contain destructive information. In real-world problems, observations often contain rare but task-irrelevant information, which we refer to as distractive information. For example, imagine a robot navigating through a street crowded with strangers. Learning to reach the destination, the robot should not classify a given state as novel just because of strangers. Instead, it should ignore them to effectively reach the destination and obtain reward. Prior novelty-based exploration strategies classify the observation as novel because strangers are new and unpredictable. In order to quantify consistent state novelty in destructive environments, we need to prioritize the task-related novelty over the task-irrelevant one. To overcome the issue, we add an auxiliary value network to the common RL scheme. The value network consists of two sub-networks, compressor and value predictor. Motivated by minimum description length principle, the compressor encodes observation to a compressive latent code. As a result, rare observations are encoded to a lengthy code, and common observations are encoded to a shorter code. So we can use the code length of latent code as proxy metric for rareness. It also discards as much information from the observation to filter out the task-irrelevant information. Of course, we need to prevent the compressor from discarding task-related information. The value predictor regularizes the compressor to preserve task-related information required to predict the state value. We propose three objective terms to learn such latent code Z. First, minimize entropy term for minimum average code length. And second, minimize negative conditioner entropy for discarding information. The two terms together form mutual information between observation and latent code. Third, maximize mutual information between latent code and state value value Y. To preserve task-related information, first we obtain well-known information bottleneck objective function defined by observation, latent code, and state value. The intrinsic reward function is the per instance mutual information between the current observation and the latent code. Since the mutual information is interactable in general, we use variational approximation proposed by LMI in his paper, Deep Variational Information Bottleneck. For the proof of concept, we perform static classification to see whether our intrinsic reward consistently ignores distractions. Each heat map shows novelty measure of test images on different exploration methods and different distraction types. Y and X-axis indicate proportions of target images and the distractions in the dataset. An ideal novelty metric should reflect only the proportion of target images, as in the red arrow. Heat map of our method resembles the ideal one, while the others don't. Here, we test on a customized grid word called treasure hunt. We visualize the learned representation of policy network using GradCam, where red color indicates high gradient activation. Before receiving external rewards, policy consider all visual information leading to the same task-agnostic exploration as in the baselines. As experiencing more external rewards, the policy focus on task-related information, demonstrating adaptive strategies for exploration. The adaptive exploration leads to superior episodic rewards. The red plot is our method. We also test on 3 Atari games on 2 different settings, with and without destructive information. Interestingly, our method performed better or equal not only in destructive environment, but also in the original Atari environments. Thank you for listening.
The next talk is entitled Dynamic Weights in Multi-Objective Deep Reinforcement Learning, and Axel Abels will be presenting.
Okay, so we're dealing here with multi-objective reinforcement learning. So this means that instead of having a scalar reward, as you would have in typical reinforcement learning, we're dealing with a vector-valued reward. So if you have this vector-valued reward, you can assign an importance to each of its components and build a weight vector W, which you can then use to weigh the reward and try to maximize the weighted return. Now, often when you assign an importance, it's likely to change. So we looked at dynamic weights, wherein the importance WT changes over time, and so you need to quickly adapt to the changing weight vector to perform well. In addition, we looked at high-dimensional problems, which typically require function approximation and which take a longer time to converge. So to tackle this, we started out from the condition network. So this is the network we proposed, wherein we added a weight input to the network, which allows it to output values which are dependent on the weight vector you're training the network on. So then the question is, how do you train this network? There are multiple alternatives. So the first naive approach would be to train the network on the current weight vector WT. So in that case, you have good convergence on the current weight vector, but you're likely to forget previous policies you've learned. So instead, we could just sample previously learned weight vectors and then train the network on them, but then you have a less effective convergence on the current weight vector. So instead, what we did was we computed the loss as the average of both previous losses. An additional problem is when you deal with a replay buffer. So replay buffer in deep reinforcement learning, you add the experiences in a first-in, first-out manner, which means that it will be heavily biased towards recent weight vectors. So this means that if you are trying to maintain past policies, it will be challenging because you will lose the experiences which are related to those previous policies. So to counter this, we proposed diverse experience replay, which essentially adds a secondary replay buffer, which will maintain diverse experiences. So in orange, we have a standard replay buffer, so first in, first out. And then in blue, we maintain a diverse set of experiences, which are much more spread across the space of multi-objective returns. So we looked at the performance compared to some other algorithms which we adapted from related settings. So here the plot is in cumulative regret, so which means the difference between the optimal policy and the policy which the agent follows. And so a lower value is better. So in our case, our CN algorithm is the blue line, and so you can see that it performs quite well compared to the other methods. And this is when weights change regularly. So after each episode, the weight changes. And despite this, our method is able to continuously learn. And then we also looked at less regular weight changes. So in this case, the agent is more likely to overfit the current weight vector because there is more time between weight changes. And so in this case, the diverse experience replay is crucial, as you can see by the dashed lines which plot the performance with diverse experience replay. So that's it. The poster will be number 49 from 6:30 to 9 p.m. Thanks for listening.
All right, and the last talk of today's session will be fingerprint policy optimization for robust reinforcement learning, and Supratik Paul will be presenting.
So say we want to learn a policy to fly a helicopter. Now, the performance of any policy is going to depend critically on certain environment variables. So for example, wind conditions here. And these are essentially state features which are unobservable to our agent and are controllable during learning. So for example, if learning is done in a simulator, but not during execution. Our objective is to find a policy that maximizes the expected value. Here, the expectation is taken not just over the transitions and the actions, but also over the distribution of the environment variable. But to be able to do so, we need to accurately take into account certain rare events. So for example, certain rare wind conditions might lead an otherwise perfectly good policy to crash the helicopter. So a naive application of policy gradients in this setting looks like this. We sample some trajectories following some policy pi. And for each of these trajectories, The environment variable is randomly sampled from the original distribution PEV. The problem with this is every time there's a rare event, the random sampling might not see this often enough. And because the gradients are computed using a Monte Carlo estimate, the Monte Carlo estimate has a really high variance. So our policy gradient is pretty much doomed to fail because it'll converge to some suboptimal policy that does not take into account these rare events. So the key idea behind fingerprint policy optimization is to not sample from this original distribution for environment variable, but to sample it from some other distribution, Q Xi EV, where Xi are the parameters of this distribution. And at each iteration, we select the parameters Xi such that it maximizes the one-step expected return. Now, the policy update can be given as the updated policy pi prime is simply the old policy plus some step along the gradient direction, which means that we can write the value of the updated policy, j pi prime, as a function that takes as inputs pi and the sampling distribution for the environment variable Xi. So concretely, we model this, the value of the updated policy as a Gaussian process with inputs pi and Xi. And at each iteration, we use Bayesian optimization to solve this optimization problem to select psi. Now, this leads us to a problem that with large neural net policies, pi is often very high dimensional, and Bayesian optimization does not scale well to high dimensional settings. So our solution is to replace pi in this GP with a low dimensional representation, which we call the policy fingerprint. The key thing to note here is that the fingerprint only needs to disambiguate between policies. It does not actually need to be a very good and accurate representation of the policy. And with that in mind, we propose the state and action fingerprints, which are simply Gaussian distributions fitted to the stationary state or action distribution that is induced by this policy. And this might seem like a really simple thing to do, because in general, these distributions are not going to be Gaussians. They might even be multimodal. But as we show, this is great for the purposes of solving the Bayesian optimization task that we have. Here are some results. We ran some experiments with some modified Mujoko environments, and we basically show that FPO takes into account these rare events and performs far better than quite a few of the baselines, including the naive approach, which pretty much does the worst of the lot. So if you want to know more, come and check out our poster later today. It's poster number 50. Thank you.
That concludes this session. 5 minutes early. If anyone else wants to give a 5-minute talk, you can. This is your moment. But otherwise, we're done. There will be another DeepRL session tomorrow.